team over here at NREL. I've been working on implementing a new compute module into SAM that's going to estimate the PV losses due to snow coverage, which Nate mentioned earlier in the morning. So, as some of you may know, snow coverage on PV arrays is actually a very significant source of loss, depending on geographic location and, of course, the type of PV system that's being employed. PV losses due to snow coverage can even get up to PV losses can approach values as high as 25% of the total annual energy production for that system. So clearly, snow is something that needs to be accounted for. Unfortunately, there's a large margin of error in actual snowfall predictions. This is because of the large ratio between general snow or general rainfall compared to the equivalent amount of snowfall. It's something on the order of 1 inch of snowfall will, or I'm sorry, 1 inch of rainfall will equate to about 1 foot of snowfall. So there's a large margin of error, especially in terms of when you're talking annual timescales. In addition to that, the actual physical dynamics of snow coverage on PV panels are not simple. It's not simply a direct relationship between the snow depth on the ground compared to the PV production of the panel. So we have implemented a new compute module in SAM. This is a model that has been based off of one that was developed by Bill Marion. It's a snow model which is meant to estimate, once again, the amount of energy loss that a PV panel will have depending on the snowfall. And the module is meant to calculate the snow coverage, and it's based off of the time since the last snowfall, the ambient temperature, and the plane of array irradiance. The model treats snow sliding as the dominant snow removal process. This is something that's been backed up by literature. There are, of course, other snow removal processes, such as snow melting or being blown off by wind. However, sliding has definitely shown to be the dominant process. So in developing this compute module, we wanted to make it easy to invoke in SAM, and that's something I'll go over briefly. We spent a little bit of time validating the snow model against some measured systems, which suffered from snow coverage. And finally, we did an investigation into trying to generate some national trends, at least across the continental United States, for how snow can affect PV systems. So real quick, just as a quick description, here's a diagram of a PV array. Over on the left, you see the height of a PV array. So this is when you have multiple modules connected together inside of one row. So from this point on, when I'm talking about the snow coverage percentage, I'm talking about the percentage of the PV array which is covered along that axis that I've labeled height. And the way the snow model is working is that if a single string, and the way the model is assuming that an entire row at the bottom of one of these, as you can see in the picture, is a single string. And if a single string is even remotely covered by snow, then the entire string is shut down. So snow is expected to, after snow has fallen onto a PV array, it's expected to slide down the array and collect near the bottom. And there's going to be slight differences between a model, or rather there's going to be slight differences between a PV system which is roof-mounted versus ground-mounted. And that's because ground-mounted systems usually have much more clearance down by the base, and so snow coverage will be removed quicker. And currently in the snow model, only roof-mounted systems are being accounted for at this time. Okay, so using the model in SAM is fairly simple. The old shading page has been renamed to Shading in Snow. If you click on the Shading in Snow page, then down by the bottom, there's a new selection for activating the snow model. It's just a checkbox in this case. It's of course only going to work if you have snow depth data inside of your weather file. The snow depth data, just like the weather file itself, can be either hourly or sub-hourly. And if you don't have snow depth data in your weather file, we've also included a macro with the latest release, which can take a weather file and take snow depth data from two separate files and conjoin them to a single file. And so as soon as you have that, all you have to do is activate the snow model by means of this checkbox, and you are good to go. So here's a flow chart of how the snow model is working. I'm not going to spend too much time going into this in detail because I don't want to take too much time away from talking about some of our results. However, just to briefly go over it, Sam will calculate, or rather once the simulation begins, Sam will, for each time step, be that hourly or sub-hourly, Sam will calculate how much energy is expected during that time, and in which case it'll go into if the snow model has been activated, the snow model will first ask, has a new snowfall been detected? If it has, the PV coverage, or the PV array is assumed to be completely covered by snow, and we will deduct the appropriate amount of energy from the previously calculated energy production, which in this case would be 100%. And then we go to the next time step, and then Sam will again calculate the expected energy for the next time step. However, if a new snowfall was not detected, we then ask, was there a non-zero snow coverage during the previous time step? If there was, we're not going to deduct any energy from the previously calculated energy production, and then we'll just go on to the next time step. If there was a previous amount of snow coverage, then we're going to ask if the current temperature and plane of array irradiance is sufficient to allow snow to slide. If it is, we will decrease the coverage slightly, and this is going to be a function of the system's tilt. And if the temperature and the plane of array irradiance are not sufficient to allow snow to slide, then we'll just maintain whatever snow coverage was on the system from the previous time step. And we will then go into deducting the appropriate amount of energy from the previously calculated energy and continue in that fashion. So an important outcome of this is if you do activate the snow model and the snow depth data in that weather file is all 0 centimeters for the entire year, then the snow model is going to have zero effect on the entire on the end result of the simulation. Okay, so we did a little bit of validation, and this is an example from that study. This is looking at the Forrestal system, which is a system in Washington, D.C. on the Forrestal building. This is a fixed tilt system. It's actually a 0-degree tilt system. And as you can see, or rather, so in the graph that you can see, we have 3 bars. The blue bar represents the amount of energy which Sam is predicting with the snow model activated. The green yellowish bar is representing the actual measured data from this system, and the red bar is representing the amount of energy which Sam predicts without activating the snow model. The numbers on top of each of the 3 sets of bars is indicating the number of hours that had snow coverage, that had some non-zero snow depth or non-zero snow coverage. So as you can see, January, February, and December all had snow coverage while the other months did not. February specifically had the most. The scaling factor in the upper left corner, by the way, is just a little bit of scaling that we did to try to isolate the effects of the snow model. And that's something that's covered in much more detail in a report that will come out shortly, which I'll mention at the end of this presentation. As far as the validation goes, if you look specifically at January and December, you can see that activating the snow model brings down the estimated energy to a much closer value to the measured result. If you look in February, you can definitely see that while the model is definitely improving the estimation, it's definitely over-predicting by quite a bit. So this isn't a perfect model, but nevertheless, this model was never really intended for time intervals around monthly or shorter time periods. and instead it's only meant to be accurate on annual timescales. So, in which it's in our 3 validation studies looking at the Forestall system and also 2 other systems in the Colorado area, the SNOW model has been shown to significantly improve annual estimations, annual energy estimations. So moving forward, after validating our system, at least against 3 systems that we had available to us, we wanted to conduct a national study. Then we used the TMY2 data set, or rather we actually used the historical data set underlying the TMY2 data set. This is the NSRDB's 1961 to 1990 data set. This is just a collection of weather files from each of the years between 1961 and 1990. And this is for 239 locations across the United States. This is a very useful data set in that it contains weather files, which we can use in SAM, and it also includes daily snow depth values. So in conducting the simulation, we just used a basic system that's very common in the PV industry. We just decided to use a basic fixed tilt system using all the defaults in the SAM 2015.1.30 version. And the only difference between each of the simulations was we imposed a tilt equals latitude rule, which is again common in the PV industry. And this actually helps because one would expect a lot of snow losses in the northern states of the country. And since these are the states with higher tilt, rather higher latitudes, they're also going to have higher tilts, which will speed up the snow removal process. So here is an example of the results from this study. Each of the dots you see here is indicating one of the TMY2 locations in the TMY2 data set. Not all of the locations are shown here. There's a few in Florida, for instance, which are not shown, and that's because we ran into problems with simulating those sites. Nevertheless, we were able to simulate snow losses for most of these. And the way we calculated snow losses was by first running a simulation for each year, by the way, between 1961 and 1990. We would run one simulation without the SNOW model activated, and we would treat that as what the system would be producing if snow wasn't present. And then we ran another simulation with the SNOW model activated, and we subtracted the simulation with the SNOW model activated from the simulation without the SNOW model activated, and then we were able to calculate how much energy snow was actually removing from the potential production from that system. And as you can see here, or rather as you can see in this plot, it's a very intuitive trend. The northern countries have much higher, or rather are expecting much higher snow losses than the southern countries. Furthermore, out towards the west, where you have higher rainfall, we're also not expecting much loss percentage, or at least as much percentage losses. One interesting thing about this trend is certainly how high the percentage losses can reach. We're observing through our simulations losses upwards of 24–25%, which is fairly surprising. We're also seeing how the snow loss trends can extend down into this range over here, the northern Midwest. And also is interesting looking down here in the mountainous regions, how high altitude regions can also experience significantly higher snow losses compared to locations right next to them. So a good example of this is Prescott, Arizona, right here as compared to Phoenix, Arizona, right next to it. Prescott, Arizona is probably around 11 to 12% expected losses, whereas Phoenix, Arizona was much closer to zero, as you would likely expect. One note is that the plot that we have here is only intended for south-facing fixed tilt equals latitude systems. This isn't intended to be for single tracking systems or any other systems. So so I guess this would be useful because if you were trying to install a PV system in one of these areas, you could use a plot such as this as a starting point to estimate how much of your PV system will lose due specifically to snow coverage. This second plot that I have here is all the same data from the plot right before it, only I've gotten rid of the geographic location data. All I've done is for each year, I've plotted the percent loss, and that's calculated in the same manner that I mentioned earlier. And on the x-axis, I plotted against the sum of the hourly snow depths. So this is just taking the array of the snow depth data and just simply summing it all up. And in doing so, doing that actually helps to maintain both how much it snows and also how long the snow is present. And it contains both of those parameters by doing that. And this is an interesting plot because it shows, once again, it shows an intuitive trend how the higher sum of hourly snow depths that you find, the higher percent loss that you can see. And this could be useful if you're at if you're trying to install a PV system in a location which is not included in the TMY2 dataset. But if you do have access to snow depth, you may once again be able to use this plot as a starting point to sort of estimate how much, or at least get a range of how much snow depth you can, or how much energy you can expect to lose specifically due to snow depth. I tried to fit the data, as you can see. I've included a function. This is just a best fit curve. There's no underlying physics which have gone into developing this equation. It's just been a best fit curve which I came up with myself. And just by visual inspection, you can see how the range of expected percent loss extends to about plus or minus 50% of wherever this red line is falling. And once again, this is only meant to be valid for south-facing fixed tilt equals latitude PV systems. So just a little bit more information. There's been a lot more work which has gone into developing this snow model, which we do not have time to get into during this presentation. However, if you are interested, we will soon be coming out with a report which will be titled The Integration, Validation, and Application of a PV Snow Coverage Model in SAM. That was written by myself. And if you would like any more information, please feel free to reach out to either myself or Janine Freeman. Thank you very much, and if there are any questions, I will be happy to take them now.
Great, thank you, Severin. Reminder that if you do have questions, you can type them into the chat box. And we have a question here in the room.
So Severin, this is Nate Blair. I had a quick question. The graph you showed for all the various locations is for tilt equals latitude, south-facing systems. So a lot of systems now are kind of typically put in at 20 degrees. That's the default in PV watts, for example. Not holding you to your answer, but what would you say would be the impact on that chart of actually decreasing the tilt? Because I would think northern latitudes have maybe a 40, 45 degree tilt, and if you lower it down, it could exacerbate the problem. Do you think that that's probably likely, or?
Well, that's exactly right. So the reason why we chose the tilt equals latitude systems is because it does facilitate faster snow removal in the northern areas. If you were to impose the 20 degrees for the northern areas, yes, snow would be removed slower, which would probably result in higher annual losses due to snow coverage.
Okay. Thank you.
We have another question here about what the impact would be for tracking systems. And to extend that, does the model currently deal with one-axis tracking systems?
So in the validation study we used, we actually looked at a system called the Mesa Top system, which is in Golden, Colorado. This is actually a one-axis tracking system, and what we saw was that one-axis tracking systems are much less affected by snow coverage, and we think this is mostly due to the vibrations and the movements of the panels themselves. How snow is much easier or removed much quicker than compared to fixed tilt systems. So snow certainly does affect one-axis tracking systems, however, not nearly as much.
can you use the model in its current form in SAM for one-axis tracking systems?
Currently, yes, you can use the model for one-axis tracking systems.
We have another question here. Have you thought about incorporating other variables besides snow depth to calculate wintertime loss?
Other variables such as, we've certainly included, or we've certainly thought about including other snow removal processes, such as, snow melting or snow being blown off of the systems. The model that we have, like I mentioned before, was based off of a model which was implemented by Bill Marion, an employee at NREL, and in his model, he only included snow sliding. However, certainly in the future, maybe it would definitely improve the accuracy of the system if we were to include other snow removal processes.
And this is Nate Blair. I'd just add that I think that as systems continue to be more and more prevalent in northern climates and kind of not traditional solar climates, other snow models will be forthcoming from other research areas, and other additional data sets will be available. At this time, we felt that Bill's model was the most robust and most validated across a broader range of locations, and was relevant for the data that we had. So the other piece is there are some models that have been developed for which typically we don't have that data in our weather files. So I think that combination is important. But as other models become available, the SAM team's always open to trying to see if we can incorporate that to give people a better answer.
Great. And we have one last question here, which is, are there plans to account for snow coverage alleviating soiling losses from dirt and soot due to snow slide and or scheduled module washes resetting soiling or snow?
Not at this time.
I think as data may become available to inform a model on that, that's an opportunity to add additional capabilities. But at this point, we're not aware of public data or development of such a model.
Okay, and one last question that's come in is, could the model more or less be used to evaluate optimized tilt angle to optimize energy output?
This is actually this would be a perfect use of this model. One thing that we saw when we were studying our one-axis tracking system was what tilt angle you set the one-axis tracking system during the night, which you wouldn't expect any nighttime dynamics to really implement or to really affect the total annual energy production. However, what we found was that if you increase the tilt angle during the night for one-axis tracking systems, you can shed snow quicker during the night. And that will just ever so slightly increase the total annual production of the system. And one final note about the system is that there's certainly a large amount of uncertainty in the model. This is why we were suggesting that the model is only really meant for annual timescales as opposed to monthly or shorter timescales.